Hello everyone, myself Devashish Das, Assistant Professor of Electronics Communication Engineering Department of Greater Kolkata College of Engineering and Management. Digital Signal Processing. In this video, we are going to study about the different topics of digital signal processing and its application, how digital signal processing can be applied in different field and how the different topics is present in the digital signal processing. We are going to study about this in these videos. Digital signal processing. This course is mainly for BTech students of electronics and communication engineering of 5th semester. The subject code of it is ECE 504. Now we take a ideal sampling and its mathematical representation. So in this representation, GT is the continuous time signal, input signal. This is the input signal we provide in the sampler. Sampler is the system where the sampling is being take place. The sampler is the system where the sampling is being take place. So GT is the input signal and G omega is the Fourier transform of this GT. And delta T is the sampling frequency. That means the frequency at which the signal is being sampled. So these two signals, the continuous input signal or continuous time signal GT and the sampling frequency omega s or delta T, is being multiplied and we get the output as a discrete time signal. This is the mathematical representation. You can see here, simply multiply, and using the multiplication property of Fourier transform, we just multiply these two signal in the frequency domain. We just get the sample signal, and if we convert into a time domain, we will get the time domain discrete time signal. In this way, we can get the sampling process or the output of the sampling is being generated with the help of mathematical representation. So in time domain, the sampling result in a continuous time signal into a discrete time signal. It is the conversion process. Sampling is the conversion process from a continuous time signal to a discrete time signal. But in frequency domain, the sampling results in multiple translations of signal spectra. Here you can see it is a continuous time signal and the frequency domain representation is like this, and for impulse train the frequency domain representation is continuous, and if we it is the sampled output, sampled signal, the sampled signal representation looks like this. In case of frequency domain, this side is a representation in frequency domain, that is the one side is omega and is another side is amplitude, and it is the time domain representation. In one case, one side is T and it is GT, or the amplitude of the signal. So it is the time domain representation, and we can see a frequency domain representation side by side, and we can get a clear understanding of the time domain and frequency domain representation of a sampling. It is a continuous input signal, it is a sampled impulse train, and it is a sampled output signal, and the representation of the frequency domain is like this. Now we'll move into the next slide. It is the reconstruction of the sample. Just we put a low pass filter in the sampled signal and we can reconstruct our original input signal with the help of a simple low pass filter along with a amplifier. Amplifier is nothing but to gain of the signal should be amplified to our desired level. Amplifier amplifies the gain of the input signal or after reconstruction of this signal, and in this way we can reconstruct the sample signal to our original signal. So it has a great impact to convert the digital signal into an analog signal also. We'll discuss it more detail in our last portion of this session. Aliasing. Aliasing is an important topic. Before going into aliasing, we just read out the statement of it. In case of undersampling, shifted version of signal spectrum shall overlap, resulting in a spectral disorder or distortion. In such cases, signal cannot be recovered from its sample. This effect known as aliasing. To avoid this aliasing effect due to spurious frequencies, a pre-aliasing filter is applied before sampling. That means the frequency of this sampling is an important role to recover of the signal also. That means the sampling frequency of the input signal is not sufficient, the recovery process is also get hampered. That is the Nyquist criteria, that if we do not sample the signal twice the frequency presence in the signal is being disrupted or distractions or distortion may appear. We can see in this picture that it is a input continuous time signal and it is the sampled signal, and the sampling rate, you can see the sampling rate over there. The sampling rate is much higher than the Nyquist criteria. That means twice the maximum frequency presence in this input signal. So we can get a good resolution of this signal, of the input signal, and for this is the first case, and in the second case we can see it is the equal to the Nyquist criteria. That means the sampling frequency is equal to the twice the maximum frequency presence in this signal. So we, in this case, we also get a moderate resolution of the signal. But for the third cases, it is the worst case where the sampling frequency is very less than the Nyquist criteria, and for this case the signal, the resolution of the signal is changed, or there is a distortion in the signal. See, in this input signal this look like this, and due to the less sampling it is the distortion occur and the shape of the input signal get changed. So LESI play a important role to avoid distortion in the input signal, or will represent the input signal in proper way like this. So the solution is the anti-aliasing filter. Anti-aliasing filter is the solution. For that, an ideal low pass filter or band limited filter, low pass filter, that it means its limit to a certain band, and it will reject the higher frequencies in the signal presence. So the distortion is not occurred in the sampler or the other digital activities. So in this way we can prevent the aliasing effect with the help of anti-aliasing filter, which is nothing but a low pass filter with desired cutoff frequency. So we'll see an animation of this aliasing process. Just have a look.
Aliasing is the effect of an insufficient sampling when a signal is digitized. The effect results in a false digitized signal with a frequency lower than that of the original analog signal. The frequency of the aliased signal can be anywhere from dc up to 1/2 of the sampling frequency. According to the Nyquist theorem, the sampling frequency must be at least twice the highest frequency contained in the signal to avoid aliasing. The Nyquist criterion guarantees that there are enough sample points to properly reconstruct the signal, provided the signal is a sine wave. Clearly, if the signal is composite and contains several frequency components, the sampling frequency must be at least twice the highest frequency component. An ideal square wave is an example of such a signal. It contains infinite frequencies, theoretically making it impossible to properly digitize.
So we have seen a animation of the aliasing effects. Now to conversion process from analog to digital, there are two more steps also there. First is quantization or quantizing and encoding. Quantizing is the breaking down analog value into a sets of finite states, and encoding is the assigning a digital word number to each state and matching it to the input signal. We'll discuss one by one about it. First, we'll discuss about the quantization process and what is quantization is, which is play an important role in our conversion process from analog to digital. So quantization is the process to converting the sample continuous values signals into a discrete value datas. That means xt is the input signal, that means after sampling is the sampled value, and that sampled value is being converted into a certain levels of the discrete value data. So here we can see a 8 steps. It is a 3-bit representation process, and due to that, from starting from 0 level up to 7, there are 8 steps: 0, 1, 2, 3, 4, 5, 6, 7. So there are total 8 steps is there, and they are quantized steps. And in this way we break this process into a discrete value data. We'll discuss it in our coming slide. Say n equal to 2 to the power n, the number of possible states the converter can output is n equal to 2 to the power n. where n is the number of bits in the analog to digital converter. Example, for a 3-bit analog to digital converter, there are n equal to the power 3, that means 8, analog quantization size q equal to vmax minus vmin divided by n. This is the step size for converting from analog to digital. So if we take a system of 10 volt, that means if a system with the input signal, which input signal is changing from 0 to 10 volt, not more than 10 volt, it is a 10 volt limited system. So the each step there will be a gap of 1.25 volt. We'll discuss it in our coming slide. We'll see how this happen. So quantization, we have 0 to 10 volt signals. Separate them into sets of discrete states, which is 1.25 volt, which we have discussed in the previous slide. So each step is quantized. For 0, we take the limit of input signal. That means if the input signal range in between 0 to 1.2 volt, it is represented at state 0. If the signal voltage is between 1.25 volt to 2.5 volt, that is represented by our state 1. In this way, we discrete or quantized the input signal in certain states. And if it is the signal is in maximum full swing range, that means it is from 8.75 to 10 volt, the signal is in state 7. In this way, we break the whole input to a certain states. It is the process of quantization, and this is the very important process. We have to break the whole analog domain into a discrete domain. You can see the whole analog range from starting from 0 to 10 volt, which is the limit of this range. The whole range is divided into 8 states starting from 0 up to 7. So in this way, we quantize the whole system. After the quantization, encoding is there. We just encoding, case of encoding, here we assign the digital value or binary numbers to each stage for the computer to read. We just assign a binary numbers for each stage of output. For 0 it is 0 0 0. There are 8 states, so 3-bit representation is sufficient to represent the 8 state starting from 0 to 7, and the binary representation from 0 0 0 to 1 1 1. For 0 0 0, it is represent the state 0. For 0 0 1, it is represent state 1. For 0 1 0, it is represent state 2, and likewise it is 1 1 1 represents the state 7. You can see the output state versus the output binary equivalent number. So this is the whole process. We will just convert the analog signal to a digital one, starting from a pure analog signal. In the stage 1, you can see a continuous analog signal. It is an important process. The whole process is being described with this picture. It is a continuous analog signal. After, first we have to sample this signal. We have sampled this signal in certain intervals of time, and the time interval is called the sampling frequency, sampling time, and the frequency is called the sampling frequency. After this sampling, it is being quantized. Here we can see represent the three states what we have discussed. See, this is the in the range of this. We take this as a quantization level. This signal is slightly higher than this level, so it is, we just put it down in this level. Simultaneously this signal is like this, and in this way we represent the whole signal to a quantized signal. See, it is a analog continuous signal, it is a discrete time signal, and the amplitudes of these discrete time signals are not digitized or not digital, but after quantization the system or signals is being quantized and it is in state of digital form. Now this quantized level is being converted into codes. See, for the first sample, it is the first sample, it is quantized in this system, and this is a code 100, and this code is being transmitted over a transmission line. See, 100, you can see this is the first sample code is being transmitted, and it is the second sample code 110, which is, this is 110, it is the second sample code, and third is 101, that is 101. You can see the whole quantized signal is being converted into a certain code, and this code is being transmitted over the transmission line or the channel, we can say, from the source to destination. In this way we can convert the analog signal into a digital signal, and the reverse process, that means from the digital signal to the analog signal, is being discussed in our coming slide. So this, in this way we can convert the analog signal to a digital signal. It is an example how the transmission is being take place for a digital signal. Here we can generate a parallel digital signal, and the parallel digital signal is converted to a serial transmissions of data. That means with the help of this parallel to serial converter we can convert this parallel data to the serial transmission system, and in case in the receiver end we just convert the reverse process, that means from serial to parallel conversion is being take place, and we can receive this parallel data and will make this, or it send this signal to the receiver. So in case of reverse conversion process, this is the reverse conversion process. We have discussed about the how the analog signal is converted into digital system or digital signal, and how the parallel digital data is converted into a serial data with the help of parallel to digital converter. Now, and in the receiver domain we'll discuss about the how the digital signal is being converted into a analog signal, because at the end of the hearing for a telephonic conversation we have to hear the voice, not the digital signals, because the digital signals are meaningless to hear but the analog signal makes sense. So in case of conversions of the digital signals, these are the parallel digital signals, and they are being converted with the help of 8-bit DAC, that means digital to analog converter, and we get a signal like this. a certain levels of signals, and this signal is being shaped with the help of this low pass filter. It is a low pass filter, a resistance followed by a capacitor. All the high frequencies are being grounded, and a low frequency will be transmitted in the output. With the help of this low pass filter, we'll just recover the analog signal from a digital signal. So in this way we can recover the digital signal, or will recover the analog signal from a digital signal, or it is a recovery process of a analog signal from the digital signal, or it is simple the digital to analog converter. So in the overview process, we'll just recapitulate or discuss the whole process, how the analog signal is being transmitted. Say for a voice telephony system, it is the analog signal produced by the microphone, and this signal is first sampled. It is the sample and hold circuit. Yes means sample, each for hold, sample and hold circuit. Sample or hold circuit produce the sample output of the signal, and they are being quantized, and with the help of ADC they are encoded into a certain codes, and these codes are being transmitted over the channel, and these binary number systems or binary digital data are being collected at the receiver end, and we convert the digital signal to a analog with the help of digital to analog converter, and at the end a low pass filter is being used to get the proper shape of the analog signal from a digital signal. You can get a discrete digital output, and with the help of this low pass filter we can get a clear shape of a analog output, which is being fed to a speaker, and with the help of the speaker we can get the analog voice output of the telephone. In this way we can convert the whole process from analog to digital and digital to analog conversions. So at the end I would like to say that the analog and digital both are important, because the whole world is analog and we have to process this analog to a digital for our transmission process, and data corrections, error corrections, they are very much easy for the digital system. So digital system also required, and along with analog system, so both are side by side systems, and we have to take care of both to get a proper communication or proper processing of the system. So that's all for today. Thank you for watching. If you have any queries, you can contact to me. The contact number is given. The same number can be used as WhatsApp number. If you have any queries or doubt, you can call me or WhatsApp me to this number. Thank you very much.